Welcome to the third and final video of the Socket Reuse series. In this video, we will finalize the Socket Reuse-based exploit and launch it against the vuln server. Let's start by writing the shellcode using the debugger's assemble functionality. Double-clicking the instruction or pressing space will turn on the assemble window. We will first start with non-modified instructions and later copy the resulting shellcode. Let's make some assumptions about the shellcode that we are about to create. We need to set up the stack in a proper way and then call the receive function. The arguments need to be passed in reverse order so that the flags come first, then the buffer length, followed by the buffer address, and lastly, the socket comes at the end. However, the socket reference is valid for the current stack pointer. If we push anything onto the stack now, the ESP will change, and the offset will not be equal to the calculated 188 hex bytes. Thus, the first thing we need to do is save the ESP value and possibly modify it so that we have a reference to the socket file descriptor saved in a register. Let's modify the exploit skeleton a bit so that it will allow us to send a second portion of the shellcode. We will add the reuse variable, which will hold the shellcode and add it to the buffer while decreasing the A buffer by the reuse shellcode length. In order to control when the second stage shellcode is sent, we will use the raw input function. Let's also add another C buffer to the second stage shellcode so that we see when it is received. Let's restart the application and launch the exploit. Now we can go through the breakpoint and use the step into utility until we are at the beginning of the A buffer. We will now start to write the shellcode. Later, we will copy it into the reuse variable. First, we need to save the reference to the socket file descriptor. Let's check if it is still in place as we expect it to be. Let's click into the dump window and press Ctrl G. Now let's examine the expected location. We see that it's there. However, this reference is valid only in the current moment. If we start to push anything onto the stack, the ESP value will be changed, and the socket file descriptor will not be found at ESP plus 188 hex. Rather, it will be somewhere else. So what we need to do is save the socket descriptor address in a register. Let's do just that by moving the current ESP to EAX by pushing it and then popping it afterward. We need to add 188 hex to the EAX value. However, we cannot do it directly, since it will cause null bytes to appear in the opcodes. Since we cannot send null bytes within our payload, we need to use a different instruction set. Luckily, we can add 188 to half of the EAX register so that the null bytes are not an issue anymore. Since this instruction is shorter, the debugger automatically fills the remaining space with a NOP. Let's execute the newly created instruction to see how it works. We can use the step into or the step over utility. We see that the ESP value was pushed onto the stack. Then it is popped into the EAX, and the EAX value is increased. We can follow the current EAX value in dump to make sure it points to the socket file descriptor. We should also remember that the ESP currently points to a location that is within our buffer. So whenever we would like to use the stack for pop-push operations, those operations will take place within the area of the current A buffer, so it is possible that we can corrupt our exploit. We should decrease the ESP so it points to an area before our buffer, where we are currently writing the shellcode. Now, let's try to execute the newly created instruction. We can see that the ESP is now pointing to the area before our current shellcode. Whatever stack-related operations that now take place will not affect our buffer, as the data pushed onto the stack will appear before it. We now need the receive data buffer to point into the area after our current shellcode. In order to do that, let's use the value of the altered ESP and alter it again so that it points after the shellcode. We will save the result value in a register to use later, as the buffer address argument for the receive function. Let's save the current ESP value into a register using the pop and push operations. Now we will modify half of the EBX register to avoid null bytes. Let's execute the newly created instructions. We see that EBX now points to the area after our shellcode. If we replace the A's with NOPs, the buffer location will be reached after executing the shellcode. Now we need to push two more arguments onto the stack, the flags and the buffer length. Let's start the setup of the stack for the function call. The flags argument will be pushed first. The flags argument is supposed to be equal to 0. Since we cannot push just the 0 due to the null bytes, we will use the XOR trick. Let's also execute the instructions so that our first argument is pushed onto the stack. We would like the buffer to be 500 hex bytes long, but due to the zeros, we are unable to simply push 500 to the stack. However, we can add 5 to the upper half of the ECX register, resulting in the same effect as adding 500 to a whole register. We can step into this instruction and see that ECX is now equal to 500. Now let's push a pointer to the buffer onto the stack, which was stored in the EBX register. Let's step into it. The last thing we need to push is the socket pointer. We don't want to simply push EAX, since we are not interested in the value of EAX. Instead, we want to push what the EAX value points to. Thus, we will use the push pointer instruction. Let's now step into the instruction. We can see the socket file descriptor appearing on the stack. The stack is set up properly. The last thing we need is the address of the receive function. Let's navigate to the Breakpoints tab. We cannot use the address of this breakpoint since this is just an address of a jump. Instead, let's double-click on the receive breakpoint so that we are taken into the disassembly view. We'll then double-click the instruction or press space to see it in the assembly window, which reveals the real address of the function. Let's copy this address so we can use it in our shellcode. Now we'll go back to the disassembly pane. We will need to push the address of the receive function that we just saved onto the stack. Due to the null bytes in the address, we will smuggle it onto the stack first by increasing every second digit of the address by 1, and then subtracting the respective value from it. Let's walk through those two instructions. We will now see that EDX points to the receive function. Let's add the call to EDX so that the function can be executed with our arguments. Since we do not want to see the receive function internals, we will use step over instead of step in. This way, we will execute the function and land right after its return. We see that the program is no longer in a paused state. Instead, it is waiting for incoming data since the receive function has just been called. Let's press Enter in the exploit window so that it sends the remaining data to the vuln server. We see that the second stage shellcode has appeared right after our current reuse shellcode. The data was received in an unmodified form in the place we wanted it to be. Let's mark the whole shellcode and use the binary copy utility to transfer the opcodes into the exploit. We will right-click, then select binary copy, and then paste it into gedit. The shellcode is not in Python format, but we can use a match and replace utility to adjust it quickly. We will change every space to a \x escape sequence. Let's paste it into the reuse variable. Now let's test the exploit for the last time before we add the shellcode to it. We'll also go ahead and restart the application. We are again at the beginning of our shellcode, which is coming from the exploit this time. Let's step over every instruction. When reaching the call to receive, let's press Enter in the exploit. We see that the second stage shellcode was properly received. That means that the exploit is working correctly. Let's add the last modifications. Let's also change the A's to NOPs so that they do not alter the execution flow in any way. We can also generate the shellcode using the MSF Venom tool. Let's copy the output payload in the place of the second stage shellcode placeholder. We'll also restart the vuln server now. Let's skip the breakpoints by running the application until it is at the receive function. Then we'll send the second stage buffer. We will also start a netcat listener now to receive the reverse shell. We see that the shell was received. Let's run the exploit one last time outside of the debugger. Now, let's recreate the netcat listener and run the vuln server. And finally, let's run the exploit. Since there are no breakpoints now, we simply give the second stage a few seconds delay before issuing. The shell was properly received. We have a working exploit that utilizes the Socket Reuse Shellcode against vuln server on Windows 7 32-bit. And this concludes video 3 of the Socket Reuse series. Thanks for watching.